What do you think about this? Is this beautiful or pretty freaking ugly? Well, it is beautiful in some sense, but doesn't this kind of get, what if J was 1? What if J was 1? Doesn't that make a little confusing? Then I have to like consider it. J is 1, J is not 1, right? And if J is 2, then I really shouldn't write J minus 1 because that's redundant, right? Do you know an operation where you could restate this definition so that it's not ugly and I don't have to consider special cases? In algebra, if I have something equal to something else and I wanted to restate that, what would I do? Isolate one side, right? How could you isolate this side and get the same thing out? What would you do if you brought this thing over there? What would end up on this side? 0. And then what would the claim of linear dependence be?
Come up with a linear combination with certain scalars so that the linear combination equals 0,
then the set is linearly dependent. But what would have to be, I can always come up with a linear combination that's equal to 0. What is it? 0, 0, 0. In fact, I can do that for vectors that are not linearly dependent. For example, the vectors, so the problem with your definition, would you agree that there's no way to scalar multiply this one to get to that one? Watch this. So you are right there on this definition, or I might call it a theorem in this class. When I was first given this definition, they just gave it to me as a definition, but my claim is this comes from some deep thought. So you're right there, I agree with you. What was the conjecture that you made for a good way to think about this kind of clunky definition? Instead of saying a set of vectors is linearly dependent, if one of the vectors can be written as the other vectors, what's a different way to say that? There exists a set of x's, there exists a set of scalars such that I can multiply all those vectors by those scalars and get what? 0, but I can always do that. So that definition isn't good enough. What's the extra condition that you would need to make in order to make sure that that actually describes what we're looking for? They can't all be 0. Okay, we'll call that a theorem. In most linear algebra classes, they call that a definition. That's where they start. But I want you to remember that when we're talking about linearly dependent sets of vectors, underneath it means one of your vectors can be written as a linear combination of the other vectors, and then we're going to do an algebraic convenience to say that is equivalent to saying what? Yep.
But does it mean that one of the scalars should be minus 1?
Well, I mean, here's if I multiplied all the scalars on the right by 2 and the left one by negative 2. Yeah. So and that's what you were getting to, right? That was the intuition that you had so beautifully, that once you have one combination, that you can actually create all combinations underneath. You're talking about null spaces from lesson 19 or 20 right now. We're going to get there. We're going to get there, right? But the intuition that you have right now is like really, really powerful intuition. It gives you, that's actually a theorem that talks about all solutions to general linear systems problems as scalar multiples of the null space, the basis vectors that generates the null space. Don't worry about anything I just said. I just said blah, 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 right? But what's the claim of linear dependence? What's the theorem say? Okay, so first and foremost, in this context of linear dependence, what are we talking about? Are we talking about a single vector? Yeah, we're talking about a set of vectors. That's different from the problem of analyzing a single vector with respect to another set, right? Okay, so let m and n be natural numbers, and then we're going to say, what do we need in order to talk about linear dependence? Set of vectors. How many vectors are we going to talk about in this class? N of them, each of which is the size m. How does that relate to the matrix vector multiplication problem? In the background, we're not worrying about it, but I want to start making the connections. If the matrix is m by n, how many columns do we have? N of them, each column is of size m. So if we say that these are those vectors, the theorem says these vectors are linearly dependent And then this is where my friend Ryan, if you were just a few hundred years older, you'd be famous for the rest of life. These vectors are linearly dependent. One of those vectors can be written as a non-zero linear combination of the other vectors if and only if what?
Set of non-zero scalars.
There exists a set of scalars, x1, x2, all the way down to xn, element of R, such that x1 times a1 plus x2 times a2 plus xn times an is equal to the zero vectors. And when we say a non-zero set of scalars, does that mean all the scalars have to be non-zero? At least one of them with at least one scalar, perhaps we call it x sub I, not equal to 0 for some what? I element of